Download this code from codegive.com, link in the description below. Alibi, enabling transformer language models to handle longer inputs. Transformer models, with their self-attention mechanism, have revolutionized NLP. However, the quadratic complexity of self-attention with respect to sequence length limits their ability to process very long sequences. This is because the attention mechanism calculates relationships between every pair of tokens in the input sequence, requiring n(2) computational resources and memory where n is the sequence length. Enter Alibi, attention with linear biases, a position encoding technique that allows transformer models to generalize to sequence lengths longer than those they were trained on without retraining or fine-tuning. It achieves this by cleverly modifying the attention scores using a linear bias term dependent on the relative distances between tokens. This tutorial will delve deep into Alibi, covering 1. The problem, positional encodings and length limitations. 2. The solution, understanding Alibi's linear biases. 3. Benefits of Alibi. 4. How Alibi works, a detailed explanation. 5. Implementing Alibi with PyTorch, code example. 6. Integrating Alibi into transformer architectures. 7. Considerations and limitations of Alibi. 8. Practical applications and use cases. 9. Advanced techniques and alternatives. 10. Conclusion. 1. The problem, positional encodings and length limitations. Traditional transformer models, like the original transformer from the Attention Is All You Need paper, use positional encodings to inject information about the position of each token in the input sequence. These encodings are added to the token embeddings before being fed into the attention mechanism. There are two main approaches to positional encoding. Absolute positional encodings assign a unique vector to each position in the sequence. The most common example is sinusoidal positional encodings. These are fixed functions of the position index. Limitation these encodings are typically learned up to a specific sequence length, max_sec_length, during training. If the model encounters sequences longer than this during inference, it struggles to generalize effectively. It hasn't seen those higher position indices during training, leading to degraded performance. Relative positional encodings encode the relative distance between tokens rather than their absolute positions. These encodings are usually learned as parameters. Limitation while they can potentially generalize better than absolute encodings, they are still typically limited to a fixed window of relative positions. In both cases, the core problem remains: the model's ability to handle longer sequences is constrained by the maximum sequence length seen during training. This often necessitates retraining or fine-tuning the model on longer sequences, which can be computationally expensive and time-consuming. 2. The solution, understanding Alibi's linear biases. Alibi offers a simple yet elegant solution. Instead of adding positional embeddings to the token embeddings, it directly modifies the attention scores with a linear bias term. This bias term is a function of the relative distance between tokens and doesn't require any trainable parameters. Specifically, the attention score between token I and token j is adjusted as follows. Where *q is the query matrix, *k is the key matrix, *v is the value matrix, *d_k is the dimension of the key vectors, *alibi_bias is the linear bias matrix. The key idea is that alibi_bias matrix penalizes attention to tokens that are further away in the sequence. The strength of this penalty is determined by a set of multipliers. This simple modification allows the model to extrapolate to longer sequences because the relative distance calculations remain valid, regardless of the overall sequence length. 3 Benefits of Alibi. Asterisk zero-shot generalization to longer sequences. Asterisk alibi allows models to handle sequences significantly longer than they were trained on without any retraining or fine-tuning. This is the primary benefit. Asterisk simplicity. Asterisk alibi is remarkably simple to implement. It only requires a few lines of code to modify the attention calculation. Asterisk no extra parameters. Asterisk alibi doesn't introduce any new trainable parameters, keeping the model size and training time consistent. Asterisk improved efficiency. Asterisk by downweighting distant tokens, alibi can potentially improve the efficiency of attention, especially for very long sequences. It implicitly encourages the model to focus on local context. Asterisk compatibility. Asterisk alibi can be easily integrated into existing transformer architectures. For how alibi works, a detailed explanation. Let's break down how alibi achieves its remarkable generalization capability. 1. Relative distance. Asterisk alibi focuses on the relative distance between tokens, i.e., I, j, where I and j are the positions of the tokens in the sequence. 2. Linear bias. Asterisk the alibi underscore bias matrix is constructed such that each entry alibi underscore bias I, j contains a linear function of the relative distance I, j. This linear function acts as a penalty, discouraging the model from attending to tokens that are far apart. 3. Multipliers. Asterisk the slope of the linear function, i.e., the strength of the penalty, is determined by a set of multipliers. These multipliers are typically chosen such that attention weights are distributed more locally as the distance increases. A common strategy is to use geometrically decreasing multipliers, explained below. 4. Attention mask. Asterisk typically, an attention mask is used during training to prevent the model from attending to future tokens, for causal language modeling, or to padded tokens. Alibi works in conjunction with the attention mask. The alibi underscore bias is added to the attention scores before applying the attention mask. 5. Geometric progression of multipliers. Asterisk a common and effective method for selecting the multipliers is to use a geometric progression, where asterisk m underscore I is the multiplier for the ith attention head. Asterisk b is a base value, typically between 0 and 1. A smaller b leads to a stronger penalty for distant tokens. Asterisk number underscore heads is the number of attention heads in the transformer layer. This ensures that different attention heads apply different levels of penalization, allowing the model to learn a more nuanced representation of dependencies between tokens. Example asterisk. Let's say we have number underscore heads equals 8 and b equals 2 caret, minus 8/8 equals 0.5. Then the multipliers would be. Notice how the multipliers decrease as the head index increases, indicating that higher indexed heads will penalize distant tokens more strongly. 5. Implementing alibi with PyTorch, code example. Here's a PyTorch implementation of alibi bias generation. Explanation asterisk. 1. Generate underscore alibi underscore bias, attention underscore mask, number underscore heads, alibi underscore scale underscore factor, asterisk. Asterisk takes the attention mask, number of heads, and an optional scaling factor as input. Asterisk calculates the relative distances between all pairs of tokens. Asterisk computes the multipliers using a geometric progression as described above. Asterisk constructs the alibi underscore bias matrix by multiplying the multipliers with the distances. Asterisk applies the attention mask to set the bias for masked tokens to -infinity, effectively preventing the model from attending to them. Asterisk scales the alibi bias by a factor that depends on the number of heads. 2. Example usage asterisk. Asterisk demonstrates how to use the generate underscore alibi underscore bias function. Asterisk creates a dummy attention mask with some padding. Asterisk prints the shape of the generated alibi underscore bias and a small section of the bias to visualize its structure. 6. Integrating Alibi into transformer architectures. Integrating Alibi into your transformer model is straightforward. You'll need to modify the attention mechanism to incorporate the alibi underscore bias. Here's how you'd typically do it within a PyTorch-based transformer implementation. Key changes asterisk. 1. Scaled underscore dot underscore product underscore attention function asterisk. Asterisk takes an alibi underscore bias argument. Asterisk adds the alibi underscore bias to the scaled underscore attention underscore logits before applying the attention mask and softmax. 2. Forward function of the attention class asterisk. Asterisk accepts an alibi underscore bias argument. Asterisk passes the alibi underscore bias to the scaled underscore dot underscore product underscore attention function. 3. Transformer encoder layer with alibi class asterisk. Asterisk now accepts alibi underscore bias as input to its forward method. Asterisk passes this bias down to the attention layer. 4. Generate underscore alibi underscore bias function asterisk. This is the function we defined in the previous section, which generates the actual alibi underscore bias matrix. It is crucial for creating the linear biases used in the attention mechanism. How to use asterisk. 1. Generate the alibi underscore bias asterisk before passing data through your transformer. Generate the alibi underscore bias using the generate underscore alibi underscore bias function. The mask passed to this function should be compatible with the attention mask that will be used during the attention computation. 2. Pass the bias to the attention layer asterisk. Pass the generated alibi underscore bias to the forward method of your transformer layer, or any attention layer that uses this modified attention function. 7. Considerations and limitations of alibi. While alibi is a powerful technique, it's essential to be aware of its limitations. Asterisk performance degradation asterisk. Although alibi allows generalization to longer sequences, performance can degrade as the sequence length increases significantly beyond the training length. This is because the model hasn't seen these very long dependencies during training and the extrapolation may become less accurate. Asterisk long-range dependencies asterisk. Alibi primarily encourages the model to focus on local context. While beneficial for efficiency, it might hinder the model's ability to capture long-range dependencies if the penalty for distant tokens is too strong. Careful selection of the multipliers is crucial. Asterisk multiplier tuning asterisk. The performance of alibi is sensitive to the choice of multipliers. While the geometric progression described above is a good starting point, it might be necessary to tune the base value, b, to optimize performance for a specific task and data set. Asterisk not a universal solution asterisk. Alibi is most effective when the task can benefit from focusing on local context. For tasks that heavily rely on extremely long-range dependencies, example document-level summarization with distant dependencies, alibi might not be the optimal solution. Asterisk potential for bias asterisk. By explicitly biasing attention towards local regions, alibi can introduce a form of inductive bias. It's important to evaluate the model's performance carefully on a variety of inputs to ensure that this bias doesn't lead to unintended consequences. 8. Practical applications and use cases. Alibi is particularly well suited for tasks that involve long sequences and can benefit from focusing on local context. Asterisk text generation asterisk. Language models with alibi can generate longer text sequences without retraining, which is beneficial for tasks like article writing, story generation, and creative text formats. Asterisk code generation asterisk. Alibi can help code generation models handle longer code snippets, improving their ability to generate more complex and functional code. Asterisk long document processing asterisk. Processing long documents, such as legal contracts or scientific papers, can be challenging for traditional transformers. Alibi can facilitate this by allowing the model to process the entire document without excessive memory requirements. Audio processing. Alibi can be applied to audio processing tasks where long audio sequences need to be analyzed. It can help the model focus on relevant segments of the audio. Time series analysis. Analyzing long time series data, such as financial data or sensor readings, can be improved with Alibi by focusing on local patterns and trends. 9. Advanced techniques and alternatives. While Alibi is effective, several alternative and complementary techniques address the long sequence limitation of transformers. Sparse attention. Sparse attention mechanisms, such as longformer, reformer, and big bird, reduce the computational complexity of attention by only attending to a subset of tokens. This allows them to handle much longer sequences than standard transformers. Linear transformers. These models aim to approximate the attention mechanism with linear operations, achieving O(n) complexity. Examples include linear transformers, performer, and Nystrom-former. Recurrence-based transformers. Models like Transformer XL introduce recurrence to maintain information across segments of the input sequence, enabling the processing of very long sequences. Sliding window attention. This approach divides the input sequence into overlapping windows and applies attention within each window. It can be combined with other techniques like sparse attention to further improve efficiency. Flash attention. An efficient attention algorithm designed to improve the throughput and memory usage of attention operations, especially on GPUs. While it doesn't fundamentally change the attention mechanism, it allows for faster processing of longer sequences. Combining Alibi with other techniques. Alibi can be combined with some of these techniques for further improvements. For example, Alibi plus sparse attention. You could apply Alibi within the sparse attention mechanism to further bias attention towards local context within the selected sparse tokens. Alibi plus sliding window attention. Alibi could be used within each sliding window to encourage the model to focus on tokens that are closer together within the window. 10. Conclusion. Alibi provides a simple and effective way to extend the generalization capabilities of transformer models to longer sequences without retraining. Its ability to bias attention towards local context can improve efficiency and performance on tasks involving long sequences. While it has limitations, Alibi is a valuable tool in the transformer toolbox, particularly when combined with other advanced techniques. By understanding the principles behind Alibi and its limitations, you can effectively leverage it to build more powerful and efficient language models. Remember to experiment with different multiplier values and combine Alibi with other techniques to optimize performance for your specific task and dataset.